Okay, so let's start the session now. Uh, we'll first start with what we left yesterday. One part of yeah, don't worry, we are still discussing that. Okay, so the decision is not final yet for that.
Okay, sir. So the thing that is said in the discourse is still not final or is it final?
No, it is still not final. Okay, when I messaged Mem, she said like she will be um, right back with me. She has not replied yet on that part. Like, what will be the final decision on that? Okay, so it is still pending. Don't wait.
Okay.
But yeah, just
Sir,
a quick note, okay? Follow on, assume that uh, the import statements, okay, need not to be given, okay, for the course, okay? If the torch import statement specifically, okay, you have to assume that the torch is already imported.
yes, sir, I assume that in every question, but the thing is, you have mentioned in every question and left one question, so it gives us
Uh,
suspicious. And the thing is, you have mentioned error option as well, so it makes more suspicious that there are five options and one is error, and every question has four options, so much more suspicious becoming.
yeah, okay. Yeah, so that's why I
Otherwise, I
said,
have,
yeah,
yes,
that's
sir,
why
I
I
had
said like,
already done the 24, but then I have changed when I see the options, all options, that and all the questions. Then I thought it may maybe got on the false question or otherwise. But yeah,
mm, okay. But yeah, just not that follow on, just assume that the imports are already done. Okay, even if it's not given in the code block. Okay.
okay,
Due
sir.
to import, we won't be creating any option that has an error. Okay. If we are giving an option that it has an error, then something that is written in the code block, that part is not correct. Okay. Usually,
Okay, not
not just not in the
not the import one.
yeah, not the import one. Okay. Any error due to the imports and all, we will not consider as an error in the options. Okay, while creating the option, if we are putting an error option, then it's mostly likely because something that we are doing in the code block that is given to you, and only in the lines that are given to you, something is wrong in that. Okay.
Okay, only logical error basically.
Yeah. Whatever
Okay,
written on the screen, in that part only, you have to find any error if there is. Okay.
okay,
So that's how you would go with any error statements. Okay. Yeah.
okay.
So okay. Any more doubts, anyone? Okay. So in the yesterday class, we are almost done with the theoretical part. Just one last topic was remaining. That was the batch normalization. Okay. So the problem was that the output that we are feeding, it's going through multiple layers in multiple channels. Okay. So every time when we do the back propagation, this output that you are going in the feed forward will also change. Okay. So that's make the training a little bit slower and the difficult. Okay, so that's the problem that we want to encounter, and that solution for that is the batch normalization. The batch means because we are generally do the batch gradient descent, so we will normalize not the entire data set, but just the batch size of whatever we have. Okay, so we just do the standardization of the input that you have. Okay, for each mini base, and in this manner, we will basically stabilizing the whole training process, and it's also speed up our training process. Okay. So benefit is it can allow for our high learning rate. High learning rate can help you converge faster, but of course, if the learning rate is very high, then it can oscillate also. Okay. It reduces the need of careful initialization. Okay. So sometimes due to the weight initialization method also, the output differs, which can slow down the training. But if you do the batch normalization on the top of that, it also helps us you stabilize the training process. Okay. And of course, it's again a method of regularization. So all these three methods, okay, these all three methods comes under regularization. Okay. So how you do it? You have given a batch data set x1 till xn. Okay. We'll find the mean of this batch and the variance of this batch using your normal formula that you studied in your stats 1 and stats 2. The mean is simply the summation of all the data points divided by m, the number of data points. Variance is just each data point minus its mean, the whole square divided by m, summation for all the data points. Then you will do the standardization, that is for each data point, you will subtract its mean. Okay, this b here because its mean is specific to the batch that you are choosing. Okay, each batch that you have will have different mean. Okay, so if you are taking a data point from one batch, then you have to take the mean and the variance for that batch only to standardize. We add this epsilon just to so that if the variance is very low, it can stabilize this denominator part. Okay. Then after this, there's one more step that you have to do. That is, it's kind of like a linear regression modeling that we are doing here. Okay. So this x hat I, this is what you will get after the standardization. Okay. You will multiply it with some gamma and add the beta. After that, whatever you will get, that will be your new data point, and that will be basically what is going to feed to the next layer. Okay, in each layer, this process will repeat. And these gamma and beta are again the parameters that are going to learn along with your weights and bias that you have already. Okay, so this batch normalization includes these two new, introduce these two new parameters to you, the gamma and the beta. Okay, so is the process clear? Any doubts? Please
Sir,
note if you
excuse me.
yeah.
The gamma and beta are common to all the batches or just for?
No, specific to one batch. Okay.
Thank you.
Yeah. So
So by gamma beta, are we referring to distribution?
not the distribution. Okay. These are the parameters that we are going to learn along with the your weights and bias. Okay. So these are again the parameter, not the distribution.
This normalization we do before passing this to the network, or
So if you have your network, like if you consider the example of neural network, okay. So once you do this forward pass for this part, okay, whatever the output you will get, okay, that output has to be do the normalized, okay, the batch normalization we will do before passing it to the next layer. Okay.
So we'll do this after activation function.
Yeah, after activation.
normally this you say batch,
Yeah.
right? Pulkit? Normally we get a data set.
Hmm.
You say batch means maybe we make out of the data set having 5,000
Yeah.
information, 5,000 records. I make every batch of 100 or 1,000, whatever it is, right?
Yeah.
That's what you're trying to mean a batch, right?
Yeah.
So this,
So
what is the difference when we need to use batch normalization, when we need to use dropout? If we give that sense, maybe comparatively we can understand.
these are all the regularization
When
methods.
we need to do, or this batch normalization dropout itself is a hyperparameter.
These are something that you have to decide on your own. Okay. So these are the methods to improve the
No,
model.
yes, we will decide. But is there any proven, uh, already proven? Okay, these are all
Uh,
the kind of data set you need to go for dropout. These are all the
no,
kind of data set you need to go for batch normalization. Not like that.
not like that.
Then better to do all three and then see what is giving better
Yeah.
result. Then, so that kind of intelligence is not available currently.
Yeah. Okay. So one change here that is more, when somebody asked about whether we do this before activation and after activation, this has to be done before activation. Okay. That is after the
So-
linear operation and before activation. In that process, it will be done between that.
Sir,
Yes.
excuse me. Sir,
Yeah.
I just wanted to ask, sir. Actually, I've missed a few sessions, previous sessions of real. So I have an idea of what activation means, activation function. But sir, this normalization, sir, can you briefly explain, sir? What does it mean to normalize the data after you have done the linear operation on it? Like, does it mean to
Yeah.
flatten the data or
So
like?
not the flattening part. It's basically a regularization method you use to improve the model performance. Okay. So what we have is basically a general problem that because of our forward pass and backward pass continuously, okay, the output between the layers will change. Okay. So this will basically slow down the training a little bit and makes it more difficult to generalize. Okay. So to speed up our training process and allowing for the high learning rate so that our model converges quickly, we do this batch normalization, which is a form of regularization method. And what you are going to do for a given batch that you have, you'll find the mean and the variance for that model. You will do the standardization of your input, okay, using this simple formula of that you have, that subtract the mean divided by the square root of variance. You'll add this epsilon to stabilize the denominator in case your sigma square is something very low. Okay. And
And
then
sir,
after,
yes, sir. Yes.
yeah, and then after that, to regain the representative power of your features, you will introduce these two new parameters, gamma and beta. That these are again the new parameters, okay, that will be learned along with your existing weights and bias.
Thank you, sir. Sir, I just wanted to ask one more thing, that the back propagation thing, it was not a bit, it was a bit not clear in the lectures to me. So, like in the TA session or live session, like have you already discussed it? So, like, or because so I can like go back and watch, or like, will you discuss it? That
Uh,
back
See, for the
propagation.
theoretical part, everything is discussed, only this part is remaining.
Okay, sir. So in the previous lectures, it is there, na?
Yeah.
Okay, sir.
So one more update. I was looking at the PyTorch documentation about this gamma and beta. So, Deep, just 1 minute. Okay. So a general starting point for the gamma is 1, for the beta was 0. Okay. And we will basically initializing them to for the whole entire data set at once. Yes, Deep Kevin. Now, what's your query?
Sir, in week two's customer churn collab, I think Prof used a
Batch normalization.
batch norm Monday, yes, sir.
Yeah.
So this is the same thing.
Yes, that is
So
the
he
same.
used this layer along with the dropout layer, right?
Yeah. In that, I think that's the only lecture in which Prof did both the batch normalization and the
Okay.
dropout.
Okay. So it is fine to be used together, both these regularizations.
It's your choice which one you want to use.
Okay.
These are all something that we decide while training.
Okay,
Which type of
whatever
regular?
improves the model.
Yeah.
Okay.
Okay. Any more doubts?
Is this regularization and normalization can be used interchangeably? They both mean the same, or
No.
they both
Regularization is different. Normalization is this technique name, okay, which is a form of regularization method. It's regularization methods that you studied in your MLT, right? One of the form of regularization was those L1, L2 norm, okay, the L1, L2 regularizer that we added in the case of ridge regression and the lasso regression. Okay. So under those techniques, it comes. Okay. So one small example here. Yeah, in doubt. With respect to the images that we are dealing with, because images have a more than one dimension. Okay. Typically here, when we are going to implement them now, okay, we will be creating basically 4D tensor. Okay. So 4D tensor, it will be in the form of B, C, W, H. Okay. Or H, W. So B will be your batch size. P, W, H are your channel width and height. Okay. So you will be having 4D tensor. So how the batch normalization happens on that case, that's the example that we are talking about here. So imagine that you have a batch size of 3, you only have 3 images. You have 2 channels. Okay, and each feature map is a 2x2 matrix for activations. Okay, so 2x2 means your width and height are 2x2. Okay, so the 4D tensor that we're going to create in the PyTorch will be like a 3x2x2x2. Okay, where this 2, the first 2 here denotes the number of channels. Okay, so I have noted down the different channels, feature map for channel 1, feature map for channel 2. Because we have 3 images, that's why each channel will have these 3 2x2 map. Okay, now in the case of images, the mean and the variance that you are going to calculate, okay, these are calculated across channels for each batch. Okay, that's the reason why I have separated these images between channels. Okay, so first of all, I will just tell how these images were actually were. They were like this 1 2 3 4. Okay, and there would be another like 5 6 7 8. Okay, so that is these two are like kind of stacked together. Okay, that was one image, as you have 2 channels, so these two are stacked together. Similarly, these two are also stacked together, these two are also stacked together, and that's how you have the batch of 3 images with channel 2. Now, while doing the batch normalization on the images, you will be finding the mean and variance across channels for each batch. Okay, so currently my batch has 3 images. So for the first channel, I have extracted all the feature maps that I had for each of my image. Okay, I will find the mean of all these numbers. Just simply add all these numbers divided by the total number of numbers. Okay, so just 1 plus 2 plus 3 plus 4 plus 2 plus 4 plus 6 plus 8 plus 0 plus 1 plus 1 plus 2 divided by 12. Okay, that will be the mean for feature map for channel 1. Similarly, that will be the mean for channel 2. Okay, then the rest of the formula will be follows as given here. Okay, so that's how you do the batch normalization for images. Is it clear?
Sir, how was the mean calculated?
You will just sum all these numbers that are there
Okay,
in one
okay.
channel.
And divide by
Okay.
12.
Yeah. Similarly, there will be another mean for this channel. Okay. So there will be separate mean for each channel here. Okay. So for each batch, for each channel, you calculate the mean in the case of images. In the case of your simple 1D data points, okay, simple that you will just sum up all those values. But in the images, it's just that you have to calculate the mean and variance across channels.
Sir, these feature maps, each feature map is a 2x2 matrix of activation, which means like they are like the activations here mean activation function, na?
These are no, these
Each
are not
feature
the
map is a matrix of activations. So I got confused. Is it activation function, matrix of activation function?
no, it's not matrix of activation function. This is the output of the transformation one we got.
Oh,
Okay, and then on that we will be applying it. Okay. Now one more process is there. Okay. So basically the dilemma between the training and the inference time. Inference means the testing one. Okay. So because the testing time, there can be certain scenarios that can happen. Like for example, if your testing data point only have one image, okay, you have only one data point, then in that case, the mean will be like just the data point itself, and the variance will be 0. Okay. So to avoid these type of scenarios at the testing time, what we do is we are not going to calculate the mean and the variance of the testing one. Okay. Instead, what we are going to use, we are going to use something called as the running average, or more formally it is the exponential moving average. Okay. We call it exponential because it is getting multiplied with some quantity that will going to increase in the exponential power, and it's the average of these. Okay. So we'll set some starting value of mu running, and similar to the sigma square running. These are the values which are going to use to calculate the or to update or to normalize my testing data point. Okay, not for the training one. So we'll initialize the mu running and the sigma square running with 0 and 1. This mu b and the sigma square b are your training batch mean and variance. Okay, using these, we are going to update our mu running and the sigma square running using this recurrent relation. Okay, that this is the older one. Okay, we will multiply it with 1 minus alpha plus alpha times the mean of my current batch, using which I will get the new mu running, which again then we are going to feed into the next equation with the next batch size to again update it, and so on for the variance also. Now this alpha here is called as the one minute. Alpha here is called as the momentum parameter. Okay. Okay, which value we typically set it to 0.1 or 0.01. But in general, the value of alpha lies between 0 and 1. Yeah. Now, any query?
Here, the batch you are saying is about the test data set.
This B is for the training one. Okay. So while we are training, okay, while we are training, we are going to calculate the mean of my training batch and the variance of the training batch. And using those mean and the variance, I'm going to update my mu running and the sigma square running. Okay, these mu running and the sigma square running are not used to normalize my training data set. These are used to normalize my test data set. Okay, so we do not use the mean and the variance of my test data set to normalize them. We use this exponential moving average. Okay, this will be done throughout the entire training. Okay, the values of mu running and the sigma square running will get updated. Like let's suppose if in the first batch my mu b is let's say 5. Okay, and alpha I have chosen is 0.1. So it's 0.1 times 5, and 1 minus alpha is 0.9 times mu running I have initialized with 0. Okay, so my new mu running value would be what? 0.5. Okay, then again let's suppose in the next batch my mu b is 7. Okay, so 7 times my alpha value was 0.1 plus my mu running. Now my mu running is 0.5. So 0.5 times 1 minus alpha, that is 0.9. Okay.
The test data itself is being divided into batches.
No. Test it is not divided into batches. So, okay. Like you can divide it, but you are going to use this mu running and the sigma square running only to normalize your test data set for every instance.
Okay, that is, it's a cumulative value which
Yeah.
we got from the training data, and
Yes.
we will use that for the test. Okay.
Normalization of my test data set.
Okay.
We do not use the test statistics to normalize our test data set. Okay. Yes, Chandra.
Sir, what is the dilemma here?
The dilemma is that, as I said, let's suppose if you only have the one input for your test data set, and in that case, the mean will be just the same, the test data set itself, and the variance will be 0. Okay, so these type of scenarios occur first of all, and the second thing is if you are going to use the test statistics to update or normalize my test data set, that includes a little bit bias, because test data set is something that we do not want to use or for checking the improvements of my model. Okay, so if you've done MLP, if, I don't have you done MLP?
No, sir, I have not done.
Okay,
But
you
I
have
know
done that.
little bit. You can tell.
So in the MLP, when we were studying the transformers that we had, like not the transformer, different transformer that we do on the data set, the standard scalar, one-hot encoder. Okay, so in that case, we were only using the fit transfer method only on the training part. On the test part, we were just using the parameters that we learned on the training one, right?
Yes, sir. Yes, sir.
Okay,
I
so this similar thing we are doing here. It just that it's a little bit different with this extra parameter alpha, that's called as the momentum parameter. So it's used to accumulate this average. Okay. So
Okay, sir.
yes, Karthik.
I'm not able to understand this. The previous slide and this slide. Previous slide we are talking about the mu and the sigma. Okay.
This one.
Yeah, batch normalization. I understand. You, for every data point, you just normalize using the mean and the sigma using this formula.
Yeah,
and then
but
pass it on to the next layer.
Yeah.
Okay. This is clear. When you come down, now
Yes.
you say mu running and sigma running. What is the difference between that mu and this mu running? What is the difference between that sigma and then sigma running?
Okay.
Why we introduce this new?
So this mu b and the sigma square b, these are used to update your training dataset or not to normalize your training dataset. Well, this mu running and the sigma square running, these are used to normalize your test dataset. Okay.
What is the problem doing the same thing like training in the test also?
So see, we do not want to use our test statistics
because
while
there we use only a gamma and beta, right? Same
yeah.
we use it here.
No, it's not the same. It's little bit different. Okay. So we want to make use of our training statistics to transform our test dataset. Okay. So here we will be making use of our training statistics with this alpha parameters, which controls how this average will behave. Okay. I think in the next slide I have the, okay. Yeah, I have this configuration like what happens if you increase the value of alpha and whatever when you decrease the value of alpha. Okay. That's basically depends upon the adaptation part, but basically you want to use your training statistics to update your or to normalize your test dataset. Okay, you cannot directly use the test statistics to transform it as it can create bias. Okay.
Where this alpha comes from?
Alpha is the new parameter that we introduced. Okay, and that's a hyperparameter. Okay. This is often called as the momentum parameter. Okay, as it will control this momentum of how much the mu running in the previous history and the current history should be here. Okay. Now its value is typically chosen between 0.1 and either you choose 0.1 or 0.01, but its general value will lie between 0
Your
and
analogy of this train to test where we use fit transform and then fit, that is okay. But here we introduce another parameter called alpha. What it does? This is new. This is not learned.
Yeah, this is not learned. This is the hyperparameter. Okay, it's the also called as the momentum parameter, as I said. Okay, this will control the adaptation and the convergence part. Okay, so basically, if you set the value of alpha to be very high, okay, then it will be like a faster adaptation. Faster adaptation, why? If the alpha value is very high, okay, you are basically setting the 1 minus alpha to be very low. Okay, so in that case, what you are doing is you are basically paying less attention to this mu running that you are accumulating, and you are paying more attention to this current batch mean. Okay, so basically you want to focus on my current mean batch rather than what I have accumulated so far. Okay, this will help you to do the faster adaptation as you are focusing on my current direction that I am moving instead of the history that I have accumulated so far. While if you set the alpha to be very low, then basically you are putting less weightage to this quantity rather than this one.
This mu b and sigma b is learned from the training dataset, right?
Yes. Yeah. Correct. Okay. So.
And then you say this is running. How many times this will be keep on updating?
Until your training process completes for the entire batch, like for the entire data set. Once it finished, it will complete. Okay.
So for training, I can understand the normalization, but what we are doing here with the test data set, I'm not able to put that in my mind. So this is for the test data set, right? What we see
Yeah.
here.
Yes.
So so we are in parallel. Are we uh, normalizing both training and test data
No,
sets?
we are not parallelizing. Okay. So you are just calculating the mu running and the sigma square running throughout your training process. After the training completes, then you will have the learned these mu running and the sigma square running, and then they are going to use. Okay, you are
Okay,
not doing the
got,
parallel normalization.
got it.
Any more doubts?
You will be you will be demonstrating this, right, as a part of there is a
Yeah.
demonstration on this.
Yes, yes.
Okay.
But like, see, in the code, it's just one line code. Okay, so if you don't want to do like the dropout thing, then it's just the NN dot dropout. Okay, so in the PyTorch, you do not have to write all of this entire complexity of the mathematical calculations. Okay, it's just one line of code. So
No, unless we understand this, you will not be able to appreciate what those libraries
see,
are doing.
these are basically used to just to improve the model performance and just speed up the training process for the generalization part. Okay. Now, final one thing that is about the bias correction. So as we start the mu running and the sigma square running with the 0 and 1, okay, so that will introduce one bias because we are starting with these values, okay, and to get rid of this bias, what we do is we do this scaling of our mu running, and same thing for the sigma square running also, okay, where this t is the training step, okay, how many iterations you have done. Now, this is just to so that the initial updates that you will get, okay, that will have some bias that will get introduced because of this initialization that we are doing here, okay, and to get rid of that, we do this. Now, as your training process, this t value will become high, okay, and this t is the power of this 1 minus alpha. Alpha is quantity which is between 0 and 1. So 1 minus alpha will be quantity which is going to between 0 and 1. When you are going to increase the power for a number which is between 0 and 1, then what will happen? It will tends to 0, right? Okay. So in that case, this will be just 0. So after certain training time step, okay, this quantity will go to 0, and then your mu hair training will be equal to just mu running. Okay. So this step is just we do to reduce the initial bias that we are introducing due to this. Okay. Yeah. So that's all about the batch normalization. Any doubt here? In anything whatever is studied?
This augmentation, how we are doing?
The augmentation was that we are just creating different sample for our original input image. We can either rotate it.
Original, you create mini, and then what we will do with this?
This is again a regularization method. This is used to increase the data size. So in general, the deep models that you have, the more data you feed into them, the more better they give the performance. Okay. So to
So in other
increase
words,
data,
if I've taken a picture with an angle, so models are inverse, so it should be able to recognize the object.
yeah.
So every picture I can take 360-degree rotation and then make many
Yeah,
multiple
and not just
pages.
360 degree, not in any rotation, translation, you can add some noise. Okay, you can darken the image as long as the label that you are using does not change. Okay. So for example, if you have the MNIST data set, the example that I took yesterday, the image of 6, you cannot rotate it vertically. Okay, you cannot flip it vertically, otherwise it will become 9. Okay.
Yeah,
This
label
motion
has
is
to be
steep.
same. Yeah.
So just be careful about what type of transformation you're doing on the images. As long as your label is not changing, you can do any type of augmentation technique.
So the second picture on the first row, right? That is not allowed for MNIST because 6 will become
Yeah.
9. But
Yes,
here
correct.
cat remains a cat, so it's okay.
Yeah, yeah, it's okay.
And where do we store all this?
These are again stored in your original dataset that you have. Okay, just store all of these pictures, new pictures into your original dataset. You can train it and feed it through your network.
So if I have, say, for example, 100,000 images, then this kind of translation will make another million or.
See, in general, it's very hard to get a large data set specifically for the image, that to the labeled image. It's a little bit hard to get, and it's expensive too. So 100,000 images, such that they are labeled also, it's hard. Okay, that's the reason why we do this process.
For example, in an organization, employees, their photo, an organization having 100,000 employees, it will be available, right, to recognize. And the label
Sorry?
will be there with the name A, B, C, D.
See, what's the okay, but that's like a different persons that you are going to have. So I think you are talking about in the case of the face recognition data set, but that's a different way in which we do the training for that.
Or for any policing, right? A number of criminals. ID and this one will be there. The organization.
Yeah, but you cannot get every kind of data set, right, for your training process.
Okay, space will be a problem. We need to manage that. Okay.
Not just a space, getting the data in hand, it's not so easy as it seems. Okay, collecting the data information, you should not violate any kind of privacy because it's the images. So of course, it concerns the privacy also. For the privacy of the person that you are, the image of the person that you are using.
Of course, privacy.
So there are many things that are involved. Yes, Chandra.
So this noise added, is that a backend process or something?
No, it's like kind of we will just modify a little bit our pixel values. So like few of the pixels I can modify here and there. Okay, just a little bit few. So in that case, it's like get some kind of noise. So make it a little bit different from the original image.
Okay.
Okay. Yes, Shubhra.
Yes, sir. This data augmentation, you said, is a type of regularization, right?
Yeah.
So, sir, like this is done on like this regularization thing you said. When is it done on the data, like on the like in the on the training data in the feature space, like during convolution or like after that?
Before
Like,
starting the training, that documentation is done before starting the training. Okay. So let's.
So I guess the main reason is for the model to generalize well, right? So
Yeah.
if we are kind of done this kind of stuff, right? Rotation means if somebody has taken a picture from an angle. The whole idea of cropping or zooming is if I have some kind of partial view, brightness, based on the camera quality and all that kind of stuff. So all these operational noise should not hamper the ability of the algorithm to detect whatever is the object of interest or classify in this case, I guess, cat versus dog.
Correct. Okay. Let's wrap this up for now and move on to the collab. So this is the collab that I'm going to use it for today's session. I've pinned the link. I hope my screen is visible.
Yes, sir.
Yeah, so the content for the collab will be what Prof has discussed, starting with implementing the convolution layer and the pooling layer without the use of PyTorch. Okay, specifically the PyTorch modules that we have, the nn.con2d and the nn.maxpool2d. Okay, specifically we are not going to use them while implementing the end visualization of these two. Visualization, we are just going to use the matplotlib. After that, we will see how we can implement them using PyTorch. And then after that, we'll move on to creating a simple CNN structure, okay, for the fashion MNIST dataset, and a little bit data pre-processing part and the loading part for the fashion MNIST. And then finally, we are going to just do the training cycle. The training cycle part will remain same, like what we did for the case of NN model, okay. There's nothing going to change in that part. Yeah, so let's start. First with importing necessary libraries. So we need NumPy and we need the matplotlib. Okay. So we are going to import them using NumPy and the matplotlib.pyplot as well. Okay. So yeah, let's create a function. Okay. So for the convolution, I'm going to create the
Can you
function
increase the, if it's possible, can you increase the size?
font size. Okay.
Size.
Is it okay or should I increase more?
As best as you can.
Is it okay now?
Yeah, better.
Okay.
Yeah, that's fine.
Yeah, so currently this function is not going to take any parameters. Okay, so basically we are going to define the input and the kernel inside this function itself, and then we are going to use the input and that kernel to do the convolution operation and then visualize. So I am going to create one input X. So that is a array. Okay, this is basically a matrix. So currently I am creating this one. Okay, in which the first three columns are the columns of 1 and the next three columns are columns of zeros. Okay, so this is basically create kind of like an edge in the vertical direction. Okay, 1 2 3 4. Five and 6. Okay, so this is a 6x6 input image. Okay, it's a 2D image. Now, if you just want to visualize this image, then you can use the plt.imshow function. You can pass your X. Okay, now there's something called a CMap in the matplotlib, this em show function. Okay, so what type of coloring you want to give to this your input image. Okay, so if I like do not, or I think with the gray. Okay, let me call this function also. Not capital I. Okay, then this is how it is going to generate. Okay, the white part and the black part. White part for these ones that you had. Okay, these initial 3 columns that you had, these are your white part. Okay, the black part is coming from those zeros. Okay, now if you want, you can change this CMap to where it is. Okay, now I'm going to use this color mapping here because otherwise that white part that you had will go mix with this white part. Okay, so that's why I'm going to use this color mapping. So yellow is for the 1, 0 is for the violet. Okay, I hope so far so good. Now, the next part is I'm going to create one kernel here. And that is a for a 3x3. Okay. And this kernel is kind of like an edge detector. Okay. The reason why it works as an edge detector, okay, is because if you see when you are going to place this kernel, okay, on one region of this image, okay, it will take the vertical part from the left and the right, or basically the ends of the place where this kernel is going to fit. So in this place, it's going to take this portion, okay, and separate the difference of these two. So what will happen in that case? It's going to detect an edge if there is a change of color while sliding through this kernel. So in the initial portion, okay, this 3x3 portion, everything is 1, so there is not going to any change. But if you slide it here, okay, in this portion, this 111 will get mapped with this, while this 000 will come with here. So because there is a change in color here while sliding this kernel, okay, it's going to give a different output, or it's going to like fire kind of thing. You can think like it's going to fire an output in that case more strongly rather than the one when you have all the same colors. Okay, so this kernel here works like an edge detector in the vertical form. As you are going to slide through this kernel, okay, if there's any change of color while sliding this vertically, okay, then it's going to detect that change. Similarly, you can create an horizontal kernel where you can put 111 here and negative 111 here, and the second row is just row of zeros. Okay, that's detect the horizontal edges. Okay, so is it clear till now?
Here I don't understand. 0 means you just mask, right? 1 means you just filter it out. What will -1 do?
See, you are not masking or filter it out. What you are doing is when you are placing a kernel in one place, okay, if there's no different color while putting this kernel, okay, just like in this portion, when it's going to come, everything are just 1 here. Okay, 1 means they are basically of the same color. Okay, so it's not going to output you anything because everything will be just zeros in that case. Okay, but if they are of different color like this here, okay, when this kernel is going to slide, and because we have a different color here and the different color here, okay, it's going to give you a different output.
No, why I was telling filtering and masking, because we product, right? We make 1 into 1. We make 1 into 0. 1 into 1 will be 1. So that 1 is coming. 1 into 0 becomes 0, right?
Yeah.
That's why I'm telling that 0 is mask and 1 is filter. One
See this
filter
entire,
because
yeah, but you are going to use the output of this entire operation as together, right?
yeah,
Not just
together, but we what we will do is we take the product of individual product and then add it up and then put it into one box. That's what we studied yesterday, right?
Yeah. Okay, then that's
What
the same.
what does -1 will do?
-1 is just one of the parameter here. Okay, so what it's going to happen, as I said, when you are going to place the kernel at a place, it's going to detect the changes from the left corner and to the right corner if there's any change between the color, or basically that's like an edge just like we have here. Okay, when it's going to slide through this part, it will detect an change in the color in this portion because there's a violet here, there's a yellow here. Okay, that part it's going to detect. And
Yeah, let
similarly,
us
when
do
you're
it.
going to more slide it,
Let us do it. We will understand by the change in color. We can see what it does.
yeah. So first, we create two variable here: input h and input w. Okay, these are basically your x dot shape. Okay, and let's also create the output height and output w. Okay, now using the formula that we have for the calculating the output height and output width, given your kernel size, input size, and strident pooling. Okay, that's basically your input height minus your kernel size. So kernel dot shape 0. Okay, kernel dot shape 0 will give me the 3 because it's a 3 cross 3 kernel. So we also had the padding of 0 here. So just to complete the formula, I am just using this 2 into 0. And then we do the ceiling, oh sorry, the floor function with respect to stride. So my stride here is 1. And then we add the +1 to it. So this was basically my formula that I had for calculating the output height. Given the input height, the kernel size, the padding that I'm using, the stride, okay. So I will get output height. Similarly, I can get output width also. But in this case, as both will be the same because it's a square image in the square filter, okay, you'll get the basically same output here. Okay. After doing this, I will create an output which will be of shape output height, comma output width, or output width, comma output height. Okay.
For output W, shouldn't you do shape 1?
Where?
When you are calculating
Yeah.
out.
So thanks for pointing it out. Though for this, it won't going to get any effect because it's a square image. But yeah, you should do 1 time with 0, 1 time with 1. Okay. So we are creating a first of all the output in which everything will be 0. Now what we are going to do is basically we are going to replace these entries of 0 with the convolution operation that we are doing, okay, using the for loops. Okay. So for I in range of output height and for j in range of output width. Okay. Now first task is we have to extract this window part. Okay, because we want to extract this window on which we are going to apply our kernel. Okay, so we need that window here. So we need the window. Okay, now that window is from I. Okay, how much it will go from row wise? It will go till the size of the kernel, right? Okay, if I am putting my kernel here, then the area that my kernel or my filter will cover, it's basically the number of columns that I have or the width of the kernel. Okay, so that's why kernel dot shape. Okay, similarly in the column wise from j, okay, till j plus kernel dot shape 0. Okay, now for the square kernel, of course, it's not going to matter whether you are going with 1 or 0 here. Okay, but how we are calculating this window is, as I'm going to place my kernel here, it's going to go till the width of my kernel, and in the height part also, whatever the height of the kernel it has. Okay, so based on that, we are extracting this window here. Once we extract this window, we are going to do the element wise multiplication. To do the element wise multiplication, you can just simply use your asterisk symbol, okay, with the kernel that you have. Okay, and after doing that, we are just going to sum these elements, and we are going to replace it with the I comma jth entry from my output. Okay, now let me return my output also to see whether whatever we are doing is correct or not. Okay, yeah, so somewhere we got cannot interrupt, or is it at a type? output height minus kernel dot shape of 0 is going to 0. Okay, what's problem with the okay, we are getting 4. That's oh, okay, got it. Here we should not put it like this. It should come in tuple. Okay, so different problem. 2 cross 3 and 3 cross 3.
It should be output like I in a separate square bracket and then j in a
Yeah,
separate.
it's
I and j becomes a
no,
tuple.
we have to add the I and j here. So I have not added the I here.
But in
Yeah,
the
now,
like
yeah.
In the output, like when you have written output I comma j,
Yeah.
wouldn't it accept I comma j as a tuple?
No. In the NumPy or even in the PyTorch version also, when you are writing it like this, it's basically denotes the row comma column entry.
Okay.
Now the mistake was because I have not written the I plus here. From I want to go till I plus this much. Okay, so that's why it was giving the broadcasting error because it was not able to multiply these two quantity which were not of the same shape.
Sir, can you please explain this for loop like once again?
Yeah, sure. So what we are running is we have created this 0 output first. Now we are going to replace these elements of 0 with the original convolution operation. For that, first we want to extract this window part on which I am applying the filter.
Yes.
So if I am going to place my filter on this position, I want to extract how many columns it's going to extract from my x and how many rows it's going to extract from my x. Okay. So if I am going to start from here, how far it will go? It will go till the size of my kernel, right? And in the bottom also it's going to go until the size of my kernel.
Yes.
Okay. So that's why we are adding start from I, go till I plus kernel dot shape. Same in the column part also start with j. Okay, and go till j plus the size of the kernel. So as the value of the j will increase.
For this 1 0 means shape 1 2 3
Shape 1 0, it's basically about the width and height of the kernel. Okay, if you are confused, we can just simply use the shape 0 because the size of the kernel is same here, so it's not going to affect. So as your for loop will increase, current value of for this j would be 0. Okay, so it's just going to take this part. Now after that, the value of j will become 1. Okay, so it will be 1 plus 3. So it will go till from 1 to 4. Now because in the indexing part, it does not cover the last part. So it's just going to extract this part. Similarly, it's going to keep moving. And then once it finished this part, it will go in the row wise part. And you can try checking it. This is exactly what you are going to do, what you are going to get. Once you do the convolution using this kernel on this image, you can try calculating this output manually also. Okay.
Yes.
Now, we are not going to return the output now. What we are going to do in that case is we are going to just plot this kernel, the image, and the output. All these three things. Okay. So it's okay. So I'm going to use a for I range 3. I'm going to use plt.subplot 1 cross 3 cross I plus 1. Okay. Or maybe I will just go from I1 to 4. Okay. So what this subplot do is basically going to create a grid of the images. 1 cross 3, it's like a row grid. Okay. In the row, there will be 3 images. So 1 cross 3 matrix you can think, in which in one place we are going to put one image. This the third element denotes at which position of this grid you want to insert the image. So as the I will range from 1 to 4. So 1 to 3. It does not start from 0 here. Okay, it starts from 1 here. Okay. I'm going to plot my image. Okay. So okay, let's plot it in one different way. What we want to plot. So we have the X also, we have kernel also, and we have the output. So three things are there. Then we have to manually plot it, because you have to anyway write it 3 different times. So loop is not going to work. Okay, then manually plot it. 1, 3, 1. PLT dot show. I'm going to plot map equal to. Okay, and I'm going to set the title for this image as the input image. To copy paste this code, paste it 3 times here. For 2 and for the 3. Here I'm going to use the kernel. Okay, what's the kernel that you have? Okay, and here I'm going to use the output. That's the output image. Okay, let's do it so far. So this is the output that you are going to get. Now let me add one more line, that is plt.access off. Okay. So what this is going to go to, that this 024 that you are seeing, it will remove this. Okay, so that we are just going to get the image. Now let me also print the output. So as you can see, your output was this 0330. Okay, so as the initial kernel was placed in this position, there was no different color in this position. Okay, so that's why the output was 0. That's why I got purple here. When you move or slide this kernel in this part, okay, there was a change of color. So that's why it gives a strong result in this case. That's why yellow here. And then you will move it one more, then it will come like this. Okay, so that again there was a change. That's why one more color of yellow. Then it will come in this last part. Okay, here of course it's not going to be any different color, so same 0. Okay, that's how it is getting used to detect the edges or change of colors, you can think. So is the idea clear how you implement a convolution operation using NumPy without the use of PyTorch?
Can we go to this plot, the second and the third one?
Yeah.
Oh, you just okay, X, okay, kernel and the output. Okay.
Previously I was thinking to use for loop, but because either like you can do it using for loop way also, it's just that you have to create a list or the dictionary storing these elements. Okay, and then you can iterate over that if you want to do it using loop manner. Okay, so that is clear. Please mute yourself. We are not going now going to implement the pooling layer with the PyTorch. Sorry, without PyTorch. Okay. Now, if you are able to understand this part, okay, pooling layer, there's nothing change, right? Okay, the only thing where it's going to change is this part. Okay, the output will not be the Windows time kernel. It will be what? If I'm applying the max pooling, then what will be the change here?
Window.max.
Yeah. Okay, that's the only place where we are going to make changes. Everything else will remain same for this. Okay, so I'm just going to copy paste the entire code. Okay, just going to now. Yes, Karthika.
In the map, what we have just done. The color coding for 0 and -1, why it takes the same color coding?
No. See, for the here you mean it's divide its color based on the different number of inputs that you are passing. Okay. Now, if you are going to see here in the next I'm not going to make use of this same input here. I'm going to create a different input. It depends upon how many different numbers are there. Based on that, it will decide it yourself. Okay. So these color coding are not fixed like it's going to take this color for the 0 and this color for the 1. Like if you see for the output, it's taking violet for the 0, but 3 for the yellow for the 3.
For the input and the output image, okay. Only the kernel, it takes the 0.
No. See, for the output also, this was my output. It has taken yellow color for this 3. Okay, while here it was taken yellow for the 1. So it depends upon the numbers that you are passing. Based on that, it will divide the different colors. So these color schemes are something that is inbuilt in the matplot. Okay, we do not know exactly how they function it. You can read through the documentation. There are different color mapping also that you can try it out.
Okay, basically we cannot believe on this as like a legend and things.
Yeah.
We have to do it.
Yeah, you can put the legend if you want, like not with respect to the color, but yeah. So for the pooling, I'm not going to use this X. What I'm going to do is I'm going to create. Okay, just like we had the torch.arrange in the PyTorch, we have np.arrange in the NumPy also. Okay, so I'm going to create a my input dataset which contains element from 1 to 36. It will not go till 37, and I will reshape it to a 6x6 input. Okay, and of course I do not need to define my kernel here. Like what I need to define here is just a filter size. Filter size that time I will just take 2. So I can replace this calculation here with just my filter size. Okay. Now in general, we use the filter size of 2 with stride of 2 in the pooling layer. That's like general pattern, not necessary you have to follow it always. Okay, so I'm going to also do the same with padding 0, stride of 2. Okay, padding 0, filter size, input size. Okay, everywhere it remains same except this part. This will become output I comma j. Oh, sorry, it's the window dot max. If we are doing the max pooling, then this will become this. Okay. We do not have a kernel, so we can skip this part. And then we only have 2, so 1 cross 2 cross 1 and 1 cross 2 cross 2. Okay, visualize COV. I have not changed it here. Visualize pool. Okay, so this was my input image. This was your output. Okay, once you apply 2 cross 2 kernel with stride of 2, and this is your output. So it's basically like if you see in this block when the first kernel is going to apply. Okay, the max color is here, the dark color. Okay, so that's why the entire block for this output is dark. Then with the stride of 2, the next one will come here. So this color was there, so that's why it got here. Okay, now instead of the max pooling, if you have to do the average pooling, it just you can use the mean here. Okay, and you will get like some kind of a smooth version. Okay, of course it might not be evident that much with this color scheme, but it's going to use a smooth version because it's going to sum all these pixel values and take the average. So that's why smooth representation will come here. Okay. So yeah, one more thing that I have to use, or if I forgot to use here, that is I did not apply the stride thing here. Okay, so I have to apply the stride here also, right? I calculated the output height and width, but we have not applied the stride here. Okay, so how you use the stride while sliding? Okay, you are basically going to skip that many rows or columns. Okay, so that's why for that logic you have to multiply it with the stride. So if I set the stride of 2, okay, So that many steps I'm going to skip. So that's why we are multiplying it with that number of strides. So let's suppose we start with the 0, 0, then I into the stride, that is just 0, and I plus the kernel size. Okay, it's going to multiply both sides. First the stride here, also then j into stride, and also stride. So if we start from 0, 0, then it will be just 0 plus the kernel size. Then here also 0 and the kernel size. When we get the situation where I is 0 and j is 1, okay, what it will do is this part will remain same. But for this part, it's 1 into the stride. So the starting point will become 2. Okay, so that's why it's going to skip this part and will start from here. Okay, that's why we are multiplying it here. And the same reason why how much times you want to move ahead in the later part also. Okay. Okay, this should happen like right plus the kernel size. Because the amount you have already skipped plus the kernel size. Okay, so is this line clear? How it's working? So let's run it. Yeah. Now the shape is correct. It's 3 cross 3. Okay. So this is how you do the yes. Abhishek, any doubt? So this is how you do the max pooling or the average pooling. It's just you have to use here mean or max depending upon your case. Now this was using simple NumPy methods. Okay, but of course you do not have to write these all things. PyTorch gives us a very flexible way to implement it. That's what we are going to see next. How you can implement the convolution layer or the pooling layer using the help of PyTorch. Okay, so let's define a function called cont2d. Okay, so this function I will do it later. Okay, now as I said that in the PyTorch it accepts basically 4 parameters: your batch size, your channel, your width, your height. Okay, so we are first going to define our batch size. So just one. Okay, that you have only one batch size, that is just one image is there. Then input image, width and height. Input height. Okay, so because later on we are going to deal with the MNIST dataset that has the image of size 28 cross 28. So we are going to set it to the same value here. Okay, you can set it to different value also, doesn't matter. Okay, now I'm going to create a random image here. I have to import the torch first. So go back here and import torch. Okay, now let's come back. So torch dot rand n. Okay, this is used to create any random image. We'll create the random image of the batch size. Okay, and how many channels you want. So just one. Okay, so in channels is basically again your depth of the image that you want to set. So as we are considering that it is a grayscale image, okay, you can set the in channels to be any other value also. Then the input width and input height. Input width and input height. Okay, so this was just to create a 4D tensor. Okay, the first element in this will be batch size, number of channels, width, and the height. After that, now we are going to create the convolution 2D layer. Okay. So it's created using the NN module. So for that, first you have to import it using import torch.nn as NN. Okay. So we are going to use that. And just like previously we used to do this, right? NN.linear. Now you have something called as NN.conv2D. Now if you look at the suggestion, you have the option of 1D convolution, the 3D convolution also. Okay. But in our course, we will be dealing with mostly 2D convolution. Okay. Now if you read this document here, at first accept the number of in channels. How many channels your image has? Out channels, it's same as the number of kernels that you are applying. Okay, so in channel is the depth of the image. Out channel is the number of kernels you are applying. Then the kernel size, the stride, the padding. These are the main parameters. Okay, so in channels is basically the number of channels I am applying. Depth of the image. Okay, then you have out channels. Okay, how many kernels or filters you are applying. Okay, so let's suppose if I apply okay, let's take this parameter as an input to the conv2D for now. Okay, so it's the number of filters. Okay, because that will be the number of channels in the output image, right? So that's why. Then just the kernel size. So kernel size also, let's take this as an input to this function. Okay, so I want to set the kernel size of, let's say, 2 for now. Okay, 3. Then the stride and the padding. So let's keep the stride to be 1 and padding to be 0. Okay, yeah. So that's all is you have to define. Initialize it nn.conv2D layer with the define the number of depth of the image that you have, the number of channels or the number of filters you want to use, your kernel size, your stride, and your padding. Okay. Now similar to your linear layer, you have to use this conv2D layer that you created. Okay, and pass your input image to this. Okay, and maybe store the output here. Okay. Now you can okay, so to verify the output, what we can do is we can manually calculate the output height and output width here if you want. Okay. But for now, I'm just going to return the output here, or maybe output.shape. Okay. So let's call this function on 2D. Okay, my out channels is how many filters I want to apply. So let's say I want to apply 6 filters. My kernel size is 3. Okay. So I should keep it dynamic here. Okay. So it has given me an output of size 1. Okay. This 1 again here denotes your batch size. Okay. So input is also a 4D tensor. Output is also a 4D tensor in the conv2D layers that we are applying. Okay. Where the first element is the batch size. Second is the number of channels that you have, because they decided output channels to be 6 here. Okay, that's why it has the channel of 6 here. 26 cross 26 is the width and height. You can calculate using your simple formula that you have, that with a stride of 1 and the padding of 0, with input image of size 28 cross 28 and kernel size of 3, you will get this 26 cross 26 input output height and width. Okay. So any doubt in this? How you implement a convolution layer using PyTorch? Okay. You just have to make use of this function. Okay. So that's clear. And I'm just going to now create another function to create the pooling layer. Okay. So in that, what we are going to do is again for my feature map that I have, okay, I am going to use torch.arrange of 1 cross 37. Okay, I'm going to reshape it to a 6 cross 6 image. But because my pooling layer also, just like your convolution layer, accept a 4D tensor, so I have to make it a 4D tensor here. Currently it is a 2D tensor. Okay, so to do that, I'm going to use the method unsqueeze. Okay, unsqueeze across the first dimension 2 times. Okay, in every unsqueeze across the first dimension method, it's going to basically add one more block outside. So if I show f equal to torch dot arrange of, let's say, 1 cross 5 dot reshape to a 2 cross 2. Okay, currently my f is this, just a simple matrix. Okay, now you can see only 2 square blocks are there. If I'm going to use dot unsqueeze method here, across 0. Okay, then just look at the square bracket. It's added one more square bracket at the end. Okay, if I'm again going to use the unsqueeze method across the 0 dimension, then it's going to add one more square block. And now if I'm going to check the dimension of this, it's a 4D tensor. Okay, with shape 1 cross 1 cross 2 cross 2. So that is batch size cross the number of channels times input height, input width. Okay, so that's the same thing we are going to do here for this input. We are unsqueezing it 2 times to make it a 4D tensor. Okay, now to do the max pooling operation, okay, you can use nn.maxpool 2D. Okay, in which you have to specify your kernel size. So let's use the kernel size of 2 with stride of 2. Okay, so that will do the max pooling for you. So let's print the result or return the max pool. Okay, I have to call the max pool on this. So, max pool, you can pass your feature map to this. Okay, that will be your output, and you can return this output. Okay, let's call this function here. Okay, so I'll get this output here. If you want to use any other pooling instead of max pooling, then you can just simply use that also. So let's say average pooling, and for that we have nn.average pooling, avj pool 2D. Okay, in which also we have the same parameter kernel size and the stride that you have to specify. Okay, output will be just average pool of feature map. Okay, I will just comment this part and return this. Okay, so is it clear till now?
Yes, sir. Sir, are there other forms of pooling also?
Yeah,
from-
there's one more that Prof has discussed. That is the global pooling. Okay, that is called as
sir.
the adaptive. Yeah.
Okay, okay. Yes, sir. Yes, sir. Please tell.
Okay. So this global pooling, that also we have not discussed it in the theoretical part, but it's basically sir is discussed in the coding lectures. Okay, so it's like global average pooling if you want to do, and it's called adaptive average pooling 2D. Okay, in which what you want to do is you will specify what size of output you want. Okay, so if I want an output of 1, then I will just put 1 here, and then if I set the output to be the global average, and feature map. Okay. Oh, okay. One problem here because of we have the integer data type here. Okay, so I have to change the data type here. Set the t type to be torch.float32. Now it will work. Okay, so this you can see you are getting one output. Okay.
Only one.
Yeah, only one because you have specified here one. Okay, so the global pooling is basically in which you will specify in what size of output you want, and then automatically it will adjust the kernel size, okay, the stride pooling, etc., so that you will get the required output. Okay. So similarly, you have adaptive max pooling also. So global max is n dot. Adaptive, we have this max pool 2D, in which also you can specify this. Output is global max of feature map. Okay. So as between 1 to 37, like excluding 37, 36 was the max, so it will just give that out.
Yes, sir. Sir, is there like a particular case where these global type of pooling is used, or like they're like generally used like with max pooling?
Generally, we use the max pooling and average pooling. If you want, in some case in which you want a specific output, you can just directly use this. Okay, so that you do not have to calculate the kernel size, etc. Okay. Yeah. So if it's clear how you implement the pooling and the padding, sorry, not the padding, the convolution, then we can just take these multiple pieces of pooling and the convolution layer together, and we are going to create this architecture of the CNN using PyTorch. Okay, this will be our architecture for our fashion MNIST image. Our fashion MNIST image is going to be a grayscale image, so that's why the input is going to be a one channel image. Okay, which will have an input size of 28 cross 28. Okay, so this input image will be a 28 cross 28 image with one channel. On this image, we are going to first apply 32 kernels. Okay, and all our kernels that I am going to apply will be of size 3 cross 3. So anywhere in the, except the pooling part, anywhere in the convolution layer, wherever I am going to apply the kernels, that will be of size 3 cross 3. Okay, and yeah. So
sorry, sir, but what is that? Sir, what is that FC layer R to the power 128?
Yeah, I will explain. I will explain this architecture first. That on the image, first I'm going to apply 32 kernels of size 3 cross 3 with stride 1 and padding 1. Okay, so I'm going to of course write that structure while implementing the CNN. Okay, after that I will get this output. Then on this output I'm going to apply the max pooling, so I will get this output. On this max pooling output, I'm going to apply 64 kernels with the same size 3 cross 3, stride of 1, padding of 1. I will get this output. On this output, I'm going to apply the max pooling. Again, on this max pooling output. Okay, so these are what you are able to see here. These are the output after doing the operation. Okay, so we apply the convolution operation on this image. We got this output. We applied the max pooling on this. We got this. Applied convolution again on this. Okay, and then we got this, the max pooling this. Then we will apply the convolution again on this. We'll get this, of course, with 128 kernels. And then after doing the max pooling, we got this output. Of course, the size has reduced quite a lot now. Okay, so we will start with the 28 cross 28. We will reduce the size good enough. After doing that, we will flatten it. So FC denotes the fully connected layer. We will flatten this input and create a hidden layer here where, with 128 neurons. So this 128, basically there are 128 neurons in this layer. So we'll flatten this output and connect it with this layer, which has a 128 neuron. After that, there will be one more fully connected layer, which basically the classification head. So as there are 10 classes in the fashion MNIST, there will be 10 neurons in this. And this layer will also be fully connected. Okay, so that's the architecture for the convolution neural network that we are going to create using PyTorch. Okay, so in the image it might look a little bit terrible, but when you are going to implement it, it's more like you are just have to write 2 lines of code, and mostly it will be like copy paste stuff for now. Okay, so it will be very easy if you are going to implement it. So should we start? If the architecture is clear.
Is it possible to take something to start with? Take something small, from there we can go to this kind of architecture.
See, the small part we have already done it here, right? How you are applying the filter on one small image.
Yeah, these are all individual, right? We have not done something from start to end. Maybe 1 or 2 layer we keep and then go to the end, classify, and then we can blow it out with this many.
See, the main problem is that CNN, when it's going to run, it will take some time. Okay, so we have to wait for that to finish. So, and then we have to again continue with the rest part. If you want, what you can do is you can cut out this short network, okay, to play around for you, okay, and then you can try training it. So that's one thing you can do. Because see, it's just that in the image part, it's looked a little bit terrible to see. If I'm going to, when I write the code, it will look pretty easy. So, first, we are going to define the class CNN. Similar to our artificial neural network, this class will inherit from NN.module. Okay. What's the first thing that we are going to do now?
Super calling the
Yeah, constructor we have to create. Okay, what's the name of the constructor function?
Init.
Yeah, init. Okay. Underscore underscore init underscore underscore. What should I pass to the parameter here?
Self.
Self. Okay. Now, what is next? You are going to call super. Okay, basically the parent constructor. Then this init underscore underscore this. Okay. I hope you guys know what is the significance of doing this. Okay, this is basically going to call the parent class constructor. That is this class constructor. Okay. Now, once we do that, we have an input image, okay, which is of 28 cross 28. Okay, it's a grayscale image. So that basically means channel is 1. Okay, so basically, if I talk about it in the terms of channel comma height comma width, it's 1 cross 28 cross 28. Okay, we'll start with self dot conv1. This is my first convolution layer, just like we did before, nn.conv 2D. Okay, one more thing, just remember while creating any class, you have to use the self parameter in the constructor. Okay. So nn.conv 2D, here you will specify the number of in channels. For in channels is basically 1. Okay, so just let me format it a little bit. Input in channels is 1. Out channels. Okay, as specified in this network structure here, we are going to use 32 kernels in the first convolution layer. Okay, we will always use here, okay, kernel size of 3. Okay, with stride of 1 and padding of 1. Okay, now let me talk a little bit one thing here. Okay, our formula that we had, okay, to calculate the output width and height was this: 2 times p, you had s plus 1. Okay, you can use the floor function that you have. Okay, this was our formula. Now, in the case if I set the filter size to be 3, padding of 1 and the stride of 1, then I just want to, I want you guys to see what will happen in that case to the output size. So WO will be fraction W input minus 3, filter of size 3. Then we are using padding of 1, stride of 1 plus 1. Okay. Yes. Now because it is denominator is 1, okay, it will be just the same thing here that we have. Okay. So W input minus 3 plus 2 plus 1. Okay. Everything will cancel out, right? You will get output size to be same as input size. Okay. So the reason why we have chosen this configuration, that filter size is 3, stride is 1, padding is 1, that in this set of configuration you will get the same output size as input size. Okay, if this is the case, then what type of padding we are applying? Same padding or valid padding?
Same padding.
Very good. Okay. One thing that you remember this, okay? So because this will be helpful while calculating the size across the images. Okay, so output of this convolution will be what? What will be the size of that?
32 cross 28 cross 28.
Very good. Okay, because as we are using 32 kernels, so 32 channels, and as we calculated just now, the input size will be same as the output size. Now, as I said it before, every convolution operation is followed by non-linearity. So we are going to introduce non-linearity here as a form of ReLU. Okay, and then we are going to use the pooling layer. Okay, with the max pooling here. Okay, and the general configuration that we had, that's the same thing I'm going to use. That is stride is 2 and kernel size is 2. Okay, and padding is of course 0. Okay, so after doing this convolution, we will get the same size, that is 28 cross 28. ReLU also not going to change the size. The size is going to change in this pooling layer. Okay, and this is going to reduce the size in half. You can try out with the formula that with this configuration, you are going to get the size in half. That is, after doing this pooling operation, the size of the image will be 32 cross 14 cross 14. Okay. So till now, is it clear? Okay. So I'm just going to repeat these 3 steps 3 times because that's what is happening here. Okay. We are just going to repeat these 3 steps 3 times. Okay. Now I'm just going to call this as conv2. This is the second convolution layer. This is the second ReLU layer. Okay. And this is the second pooling layer. Okay. Now this is the third convolution layer, third ReLU layer, and the third pooling layer. Okay. Along with that, I have to also make changes in the input channel, because now in the second convolution layer, what will be the input channel value?
32.
Very good, 32. And now because we want to set 64 kernel here, so that's also I have to change. Okay. Now again, what will be the output after pooling to operation here?
It should be 14
Yeah.
by 2.
Yeah, 64 cross 7 cross 7. Okay, so the input channel will be 64, and we want to use 128 kernel now. Okay, so again, what will be the output now after this pooling?
3.
3. Very good, because we are using the floor function. So 3.5, half of the 7 is 3.5, but floor function is 3. Okay, so now after this, we are going to flatten the image. Okay, That is, whatever the output that we are getting from this, we are going to flatten it. Okay. And we will pass that to the first FC layer. Okay, fully connected layer. And for that, we need to create a linear layer now. Okay. Now, this is the part where we have to provide it what size it should be. Okay. So that's the reason why we have to calculate all this size, because now if you are going to define this fully connected layer, you should know what is the size of the image at this position now. Okay, because only then you will be able to create this linear layer. So as the size of this layer or size of the image after this operation is, let me write it down.
128 into 3 into 3.
Yeah, very good. Is 128 into 3 into 3. Okay, so it will have 128 into 3 into 3. Okay, and I'm going to use 128 neurons here, as we discussed here that in the fully connected layer first part there will be 128 neurons. Okay, so I think Karthika, you asked in the last class why we have to calculate these sizes. Okay, these are the reasons why we have to calculate it. Okay, because while you are defining your architecture, you have to know what is the size after these layers. Only then you will be able to define it and implement it. Okay, now of course this will be followed by again one more ReLU layer. Okay, and after that you will use dropout here. Okay, now NN dot dropout is just using dropout, NN dot dropout. Here you can define your probability, like by what probability you want to drop. We are setting it to 0.5 default. After that, we will again define our final classification head layer, okay, which will contain, as the output of this will be 128, so 128 here, and because we have 10 classes, so 10 neuron, and that's the end here. Okay, so is this entire architecture clear? How we are initializing these layers? Okay. So now, what's the next function you define after this? So we first define the init function, that is the constructor. After that, what was the another function you defined generally while creating any architecture of neural network using PyTorch?
Forward pass.
Forward. Okay. Def forward. Remember, this name should be the forward only. Okay. So forward, it accepts this self and the input image X. Okay. So it's now what we are going to do is self dot on one layer. Okay, this first layer that we created. Okay, we are going to use this. Okay, pass our X to this. Okay, and store the output again in the X. Okay, and we are going to again keep repeating this stuff. Self dot ReLU 1. Okay, store the output. Okay, and again in the X. Again X is self dot pool 1 X. Okay, so these three things again will repeat with second convolution layer passed by nonlinearity, passed by again pooling, third convolution layer, third ReLU layer, third pooling layer. Now, here what we have to do is we have to flatten it. Because if you see in the layers, we have not defining the flattening part. Of course, we have defined the layer that is the linear layer that's going to be there, but we have not defined the flattening of the input part. Okay, that's going to go into that layer. That part will be defined in this forward pass function. Okay, so my X is going to be X dot view, X dot size of 0, comma -1. Okay, so a little bit touch upon this part, x dot view, x dot size of 0, -1. So the input or the output that you are going to get after this pooling layer transformation will be of size batch size, channels, height and width in 4D tensor if I talk about. Okay. So the first element x dot size 0, it's your number of batches. And the rest of the elements it's going to get stored here. So I hope you guys know what does -1 do. Next we have this torch dot tensor. Use this. It ends 1x5 dot shape 2x. Okay, so this is a 2x2 image. I can flatten it using this f dot reshape 1, -1. Okay.
It will guess the other thing.
Yeah, it will get all the remaining things because you are only specifying 2 dimension like this, this. So you already specified one place. Other place it will automatically calculate based on the number of element it has. So because it has 4 elements, you have already specified that at the first dimension there should be only 1. Okay. Then the remaining elements are like if you do the multiplication, it will be 1, 4. Because total number of elements in your tensor is 4. Okay, and you are already specifying the number of rows. So the number of columns it will automatically calculate. Same thing will happen here. We will specify the batch size that should be there as the number of rows. Okay, so we are going to basically stack the data points into the rows manner, and because we are flattening them, that's why -1. So all those things that 3, 128, 3, 3. Okay, that will get multiplied together because of this -1 here. Okay, but we store them in a matrix. Okay, in which each row will represent the input that you have for your batches, and that will be basically the flattened part of dimension 128, 3, 128 into 3 into 3. Okay, now one of the more reason why we are using the view instead of the reshaping, it's more recommended to use view specifically while you are dealing with the images. It's more like more efficient. Okay, and view was first in like reshape was just introduced now. It was not there before in I think some of the older PyTorch version. Okay, so it's now like an habit that is going on to use the view. Another thing is view creates a I think copy. There was one more difference between view and reshape that I forgot, that one of them creates the copy and one of them does not. Like one of them does not guarantee to create a copy. That I have to look at with the documentation, but mostly we are going to use view because it's more like computationally efficient. Okay. Otherwise, it's kind of working the same as you are doing with the reshaping also. Okay. Yeah. So after doing the flattening part, we are going to pass this to the flat fully connected layer first. Okay. Followed by a ReLU. Okay. After that, we will apply the dropout. Okay. And then the final output self.fc2. Okay, and return the X here. Okay. So this is how we are going to define our forward pass. Okay. Yeah, I've searched for the documentation. So reshape can create a view or a copy. Okay, so the reshape, there's no fixed pattern that whether it's going to return the same output as view or it can create a copy. So that was one more difference. Yeah. So any doubt in this implementation part for the CNN?
A bit clarification I need
Yeah.
in the flattening part. What would be the
Okay.
shape after flattening?
After flattening, this will be the shape 128 into 3 into 3, whatever you will get. Okay, comma 1 you can apply if you want.
Okay, so since we have only one image, so it will be 1 into 128 into 3 into 3.
Yeah.
Okay, all right.
If but of course we are going to train this CNN with the session MNIST, okay, in which whatever the batch size you will define, okay, that many images will come. Okay, so now run this. Hopefully there's no error. Okay. Now let's analyze our model. Okay. So for that we'll create a function f analyze model. Okay. So our model is this CNN. Okay. So what we are going to print is the model. Another thing we can print is the number of parameters. Okay, so total params is for p in model dot parameters. Okay, parameters. Okay, nn dot not nn dot parameters. Parameters. Okay. If p dot requires grade, okay, it's a Boolean thing. Okay, and we'll sum this up. Okay, okay, one more thing should come. P dot null. Okay, so in the same manner in we were calculating the parameter for the ANN, the same code is here. Okay, so for all the parameters in my model, I am checking whether it requires the gradient or not. Okay, if it requires, then I'm going to call this function p.nummel. It's basically going to extract the number of element in that. So if it is a matrix, then it will be like, for example, this. Then nummel will return 4 because there are 4 elements in this. Okay. After that, we are going to sum this up across all the parameters. So I'll get the total parameters that we have. Of course, this is going to skip the pooling layers because pooling layer does not introduce any parameters. Okay, so we can print total params. Yes, total params. Okay, now we can create one thing here, that sample input. Okay, for torch dot random integer of batch size of 1, channel is 1, 28 cross 28. Okay, so sample output. How I get the output? How will I get the output?
Batch size into 10, I guess.
No, but like in general, if you are creating any ANN model, let's suppose, then given the sample input, how you get the output? What should I do?
By passing the input, no?
Yeah, input to the model like this, right? Okay, so this is okay. So we can print the sample input. It's this sample output. Okay, detach numpy. Okay, so one thing here, that the numpy only works on the CPU tensors. Okay, it does not work on the GPU. So this dot detach method that you use here, okay, it creates a new tensor that will basically sharing the same underlying data, but it is not attached to the computational graph. Okay, if you remember about the computational graph that Faraz talked about, basically it is used to calculate the derivatives and all, okay, for the back propagation. So in general, it's calculate or capture this history, but when you are going to detach, it will remove this input that you are using. Okay, so there will be no gradient history here. No back propagation training will happen for this. Okay, it is just going to retain you the last numbers. Okay, that's why we use detach here. Okay, so that's one thing. Yeah, so let's call our analyze model function. Okay, we got one error. Okay, inverted comma should end here. Okay, we got error from there. Inverted combination got method parameter. Self dot convolution 1. This is an method parameter but expected one of. Okay, let's see. Self dot con one input channel is 1, output channel is 32. Panel size 3. Spread of 1, padding of 1. It's okay. Dot. And is also okay. 1 cross 28 plus 28. What is here? Okay. Self dot convolution of 1. Relu pool count to the R. Correct.
Hello, sir.
Yeah.
Yeah, in the sample output,
Yeah.
you are passing input, not sample
Oh.
input.
Oh, okay, okay, okay. Thanks. I think input is something that I defined earlier. Yeah, now it's working fine. Thank you. Okay, so this was my model that I'm printing. Okay, print model. This is the output for that. Okay, so it's basically, it has elaborated all the layers that we are using, starting with the first convolution layer with one channel input, 32 output channel, kernel size of 3 cross 3, stride of 1, padding of 1. Okay, now these are in tuples because how much stride you want to do it vertically, horizontally. Generally, we took the same stride. I'm not sure about the dates of NPP. I think these are after 1 week of quiz. ReLU is simply ReLU, then pooling like that we have, then the dropout and all. The total parameters comes out to be 241, 241,546. Okay, the sample output that we got. Okay, it is of shape. I should also print the shape. So print the shape. The shape of output is this. Sample output dot shape. Okay, so the shape of the output is 1 cross 10. Okay, I remember this shape because this is going to use it later. So 1 here denotes the number of batch. As you have only one batch, so 1 and 10. Okay, if you have let's say 60 images in one batch, and the output shape would be 64 cross 10. Okay, n comma d form. Okay, so this is the sample output that we got. Okay, so is it clear till now? Okay. Now, next part is the data preprocessing, data preparing and the loading. So here we are going to load our fashion MNIST dataset, store them in some batches using the data loader. Okay. So we need 2-3 things here. So these are from torch vision. Import torch vision. Import torch vision dot transforms as transforms, and we'll be needing the transformation. We will be needing the torch vision dot fashion amnesia. Okay, I think these two will suffice for now. Okay, data loaders we need. So import torch dot utils dot data dot data loader as data. Data import data loader. Okay. Anything else? Yeah. Okay. So first of all, we'll create something called like a pipeline stuff. Okay, to transform our fashion amnesia that's going to come. Okay, so we'll create some kind of transformation using this transforms that we imported above. Okay, this transforms that we imported here. Okay, we are going to use that transforms here. In that we will call this method compose. Okay, this method takes a list of the transform object that you want to do. Okay. So it's accept as a list of transformations. So the first transformation that we are going to use is transform dot to tensor. Okay, so what this to tensor do is basically it's going to convert your PIL image, pillow image, into tensor data, tensor object. The fashion amnest dataset is loaded in the pillow image formats. We want to convert them into tensor. That's why we are doing it. Okay. Now the next transformation will be transforms dot normalize. Okay.
What is pillow image?
Pillow is one library. Okay. So the images that are stored in that pillow format that we have.
Okay.
Okay. So you have to normalize this now. So here, what you are going to pass is the mean and the standard deviation. Okay, with what mean and with what standard deviation you want to do. But this mean and the standard deviation are passed in the form of tuples. Okay. Why the tuple? Because each will contain the mean of each channels like RGB. Here also like the standard deviation across the 3 channels. Okay. But because we are dealing with just a grayscale image, which is like just a 1 channel image. Okay. So we are just going to pass only one element here. Okay. So for the mean, I'm going to write 0.2860, and for the standard deviation, I'm going to use 0.3530. Okay. Now these are the some statistics for the fashion amnest data set. Okay. That is, if you are going to find the mean and the standard deviation of the fashion amnest, this is what you are going to get. Okay. So I've already pre-calculated it. Okay. So we are not doing it now because fashion amnest dataset contains 70,000 images. So take a little bit time. So that's why I'm skipping that. But these are the statistics that we are going to use to normalize it. Okay. So let me write one thing here, that pass the mean and STD in tuples as the mean and STD for all channels, like mean for the RGB channel, mean for the green channel, mean for the blue channel, like that. Okay, that's why the tuples will come inside this. Okay, so remember that. Now we have defined our transformations that we are applying. Now comes the time to define the class names that we have. Okay, so we have a list of classes that are there. Okay, in the fashion MNIST. I'm going to create this list because later on while plotting it, we are going to make use of this list. Okay, so t-shirt is there, top is there. Okay, trouser is there. So pullover is one class. This dress is another class. We have the coat as another class. We have sandal as another class. You don't need to remember if just in case it comes in the exam. Okay, you do not need to remember these. Okay, you can. It will be given if something is asked related to this. Okay. So I also have written them in another page. So I'm just copying it from there. I'll put. So these are the 10 classes 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah. Okay. So I'm going to make use of this list later on while plotting it. So that's the use of this. Now this is the part where we load the data, training data. Okay. So it comes from Torch Vision that we imported above. Okay. It has this datasets module. In that we have this fashion MNIST dataset. Okay, it will accept some parameters like in what directory you want to store. Okay, so I want to store this in the data directory. Okay, and whether you want to import the training dataset or the test dataset. So if you set that value of the training parameter true, then it will import the training dataset. If you set it to false, it will import the test dataset. Okay, now then download. Yeah, you can do the download. Whether you want to download the dataset locally on your system or not. If you set it true, it will download. Okay, and then one more important parameter, that is transform. You want to apply any transformation? Yes, we want to apply this transformation that we defined above. Okay, so that these are the parameters that I'm going to pass. Okay, I will create one copy of this here for my test data set. Only thing that I'm going to change is I will set it to false. Okay, so this is how you load it. Now for this training data set, okay, it will contain them in the pair. Okay, each data object in this will be of pair, data point or the image, comma, label. Okay, so I'm going to use this to create the batches using the data loader. So for that, I'm going to define the batch size as 64. Okay, so we'll first have the train data loader. Okay, in which we have this data loader. Okay, if you read this document, it first accepts the data set. So my data set for the training is this train data. Okay, further read what is my batch size. So batch size is this capital one. Okay, next is whether you want to do the shuffle. So yes, generally we do the shuffling for the training one, so that the order in which my data points are coming in doesn't matter. And the num workers is basically how many basically pipelines you want to run together to load the data set or to divide it. Okay, how many workers you want to run. Okay. Same loader we are going to apply for the test with the small change. Here it will come the test data set. Okay, and in the training time we do not shuffle the data set. Okay, it's a practice to do not shuffle the data set at the time of testing. Okay, so let's run it and see if it shows any error. No. Okay, good. So now if you see, there will be 4 such instances that's going to create. Because we've used two workers for training and the test dataset. Now we have loaded the dataset, and if you see the files, here it has created this data because we have set this root here to data. In that, if you see this fashion MNIST. Okay. Now there are these rows images. You will not be maybe able to make some sense from this because these are in like zipped format. Okay. But yeah, we do not care about it for now. But it is getting downloaded in my local system, not in locally, but in the current Colab environment at least. Okay, because of this download parameter. Okay, so till now, is it clear for everyone? Okay, very good. Now, let's print this train data loader. Okay, the train data loader, the train data. Okay, so the training data, there are 60,000 data points. Okay, so if you have 60,000 data points and you are using a batch size of 64, then how many batches are going to create in the training data loader? It will be simply like this, 60,000 divided by 64. Okay, so 937 full batches will be there, in which in each batch there will be 64 data points, but there will be some data point that will be left. Okay, so what will happen to those data points? Okay, if I see the LAN of my train data loader, okay, it's 938. So basically, instead of creating 937, it has created 938 batches, in which the first 937 batches will contain the full 64 data points, because it is able to create that. But for the remaining data point, that will not be full batch because it contains less than 64 batches, but there will be. Okay, this happens due to one of the parameters. I think it's in the data loader. Okay, that we have here. Drop last. Okay, so this is one of the parameters in the data loader. So if you want that the only the full batch should be there, there should not be any batch which contains less than the batch size data point that you have set. Then you can set this parameter value to be false. Okay. So set to true to drop the last way. If you have to set it to true to drop the last incomplete batch. Okay. If you set it to false, then it will not do that. Okay. So I think the default value is set to false. Okay. So that's why we are not dropping the incomplete batch. We are taking the incomplete batch here. So the 937 full batch will be there, which contain the 64 data points. One incomplete batch will also be there. Okay. Similar things will happen for the test data loader. Pros and cons of dropping the incomplete batch. It's just that whether you want the same consistent thing, okay, across the batch size that you are feeding into your neural network. Okay, that it's just your choice whether you want to drop it or not. If very few data points are there, okay, you can drop it. But if it's causing too much data loss, then you can choose not to drop it.
Make it 100 or 50 batch size so that you don't have to drop anything.
Yeah, can do that. So it's just that now it's going to be 1200, but then I think the training might take a little bit more time. But see, I'm not going to just run the training code. Yeah. So far, is it clear? Okay. Now let's observe our data set more. Okay, so def analyze previously created model. Now we create data. Okay, so in which what we are going to do is we will take one data loader here and the number of samples. So I'm just going to take the first 10 samples, let's say, for my data loader. So for that, first let me explain one thing. Suppose you have this list 1, 2, 3. Okay, I can create an iterator over this using this iter function. Okay, so what happens with this is if I'm going to call the next element on this iter, okay, it's going to give me the element from this list one by one. Okay. When this next will go give me first element. If I call this next 2 times, okay, okay, now this one will not work because it has already called it. So therefore I in range of 3. Okay, print. Okay, then it's going to give me one element at a time from this list. Okay, so we are going to use this iterator here. Okay, to extract the element from my data loader. I will create the iterator for my data loader that I have. So this is the data iter I have. Okay, and then when I call the next on this data iter, okay, it's going to give me images comma labels. Okay, because these are stored as a pair. Okay, now what will be the shape of images? Anyone? What will be the shape of images or labels here? See, in terms of width and height, it will be 28. Okay, very good. See, we have changed the batch size here, so it will be 50, not 64. Okay, otherwise your answer was correct. Okay. But you forgot one thing, that is the number of channels. Okay, so it will be 50 cross 1 cross 28 cross 28 for the images. Okay, for the labels it will be 50 cross 10. Oh, sorry, just the 10. We have the 50 and I think labels are not encoded here, so just one element. So 50 for the labels. Okay, so images shape is batch size 1 size of 1 cross 28 cross 28. Okay, now we are going to draw these samples. So for I, range of num samples. Okay, I am going to extract the first sample from this. Okay, now because it is a 4D tensor, okay, so I have to squeeze it. Okay, U double E Z E. Okay, we'll squeeze it and we will convert it into numpy because we are going to plot the images here, and for that we need the numpy array. Okay, and for the label we will just have labels for 5. Okay, so the squeezing operation, because we have a 4D tensor. Okay, so we are extracting from that, so we have to squeeze it, so that we just get this 28 cross 28 here. Okay, now we are going to use plt.subplot. I'm going to plot this into a 2 cross 5 grid. Okay, so 2 rows 5 columns, I plus 1, because as I said previously, it does not start from 0 here, you have to start from 1 here. Okay, plt.imshow my image. Okay, plt.title. Okay, for the title I'm going to print the class name. Okay, class name will come from this list that we have created. Okay, so the class names that we had, okay, in that I will pass my label, because label is something that have value between 0 to 9. Okay, so it will like an index slicing from this list. So let's suppose if the label is 2, then 0 1 2 pullover will be the class name for that I will get here. Okay, so Okay, so final thing, plt dot right layout I'm going to use. Okay, this is just to maintain the image size and the figure size across consistent. Okay, and plt dot show. Okay, so that extra comments will not appear. You can again use plt dot access to be off. Okay, exfolia. Now let's use this function. Okay, we need train data loader here. You can use any other data loader also. It's going to give me this. Okay, I should set the CMap here to be grayscale. Then it will be good. CMap spelling. Okay, so I have printed the first 10 samples from my data loader. Okay, so till now, anyone has any doubt? Okay, nice. Just let me see the chat box. So now comes the part for the training cycle. Now in this part, there's nothing more new. It's more or like the same that we did for the ANN part. Okay. So if you understood that part, then it will be easy for you. We will initialize our model. Okay, and we will set two things. Okay. What are the two things that we need now? We have to define loss function and we have to define the optimizer. Okay, so we are going to import that. Okay, we'll import our okay, that's imported from the NN itself, so we can skip that. We can just directly use it here. Okay, so for the loss function, I'm going to use the cross entropy loss. Okay. So one thing here I did not mention previously, that is if you see in the forward here, after FC2 fully connected layer, we are not applying any activation function. Technically, after this, we should apply the softmax function because that will give me the probability. Okay, and then after that, those probabilities, among those, whichever got the highest one, we predict that class. Okay, that the reason why we did not do, because the loss function that we are using, this cross entropy loss, okay, it itself apply this softmax function. Okay, so we have to pass the input to this function without applying the softmax because it internally applies it automatically. Okay, so this is my criteria for my loss function. Then I have my optimizer as NN dot sim dot Adam. Yeah. Okay, so dot optim dot Adam. Okay, so these are the two things that we need. Now in the Adam, we have to specify the learning rate and the parameters. Okay, so first things are the params. So for that we can use model dot parameters. Okay, and the learning rate. Okay, this is okay. Yeah, everything good. Now we are going to start the training process. Okay, def train the model. Okay, it accept my model. It accept my data loader. Accept my criteria. Accept my optimizer that I'm using, and the number of epochs for which I'm training. So let's keep it 5 for now because in the 5 itself, it's going to take quite a lot of time. Not a lot of time, but yes, some time. Okay, so I will create two empty lists here, train loss and the accuracy. Okay, these are used to capture the training loss and the accuracy across the entire training process. Okay, and then I will set the start time here to time.time. This is to capture the time that it is taking. Okay, so for that, import time also. In the okay, is it some background noise from my side? Okay. I think every other person is already mute. Okay, so we set the start time and we will do like how much time it is to. Okay. Now for epoch in the range of the number of epochs that we are training. Okay. For each one, we will put our model in the training mode. Okay, this is one of the important steps. First, you have to put your model in the training step. Okay. Then I'm going to calculate the running loss. Okay. This is the loss for batches that I'm going to calculate. Okay, across the batches, how much loss is there? Okay, across the batches, how many correct data points are there, and the total data points, how many were there? Okay. Now, for I, images comma label in enumerate train data loader. Okay, so the enumerate function, it basically gives you index comma value. So that's why I here was for the index, and the value, it has two things again in the value, images comma labels. Okay, so for each of these thing, okay, what we are going to do is first is we'll set the optimizer to 0 grad. Okay, we will zero the gradient. We'll store the outputs. Okay, in the outputs, then we have to call this outputs.name. Yeah, we'll store our loss. Okay, criteria, and in that we'll pass the outputs. Okay, and the true labels that were there. So outputs comma labels. Okay, then you will call loss.backward to calculate the gradients. Okay, and then after that you will call optimizer.step. So these 5 things are same as what we did in the NN case. Okay, including this also. You will put your model in the training mode. You will zero out the gradient so that it does not accumulate the gradient. Then you will create the output, calculate the loss, call the backward function on that, updates the parameters. Okay. And one more thing. Now we will update these quantities that we have created above. Okay. In the running loss, I'm going to add this item. Okay. Dot item, what it does is, if you see the output of any tensor. Okay. So let me create one.
It takes only the value.
Yeah, it does just extract the value. Dot tensor of 1 if I do and print the A. It's the tensor of 1. If I just do the dot item on this, it extract me the value. Okay, so that's why we are just extracting the value from this loss and adding it in the running loss. So one thing this now here, what we want is what is the predicted class, as if we want to check for the accuracy. Okay, that how or check it for how many correct data points were there. Okay, so in my outputs that I had, I will find the max value. Okay, but max value should I find across row wise or column wise? First of all, what will be the size of my outputs?
It is 1 cross 10, no? Or
Not 1 cross 10. It will be batch size size of 10. Okay. Previously we got 1 cross 10 at that point also I said it is right. Here we got it as 1 cross 10 because we had only one batch here. Okay. So as we have this 50 batches or whatever the batch size we have set, the output size will be 54 cross 10.
So it should be across columns.
Very good. It should be across column, not row. Okay. Because these are the 10 class among which you want to choose the maximum value. Okay. So it's like you have this matrix. Okay. Each data points is like kind of stacked in row wise. Okay. So in this row, I want to calculate. So basically along the columns I am checking. Okay. So that's why I will pass 1 here. Okay. Now, in the PyTorch, the max value returns two things: index, comma, value. So again, on this example, let's suppose I have run this torch.tensor of torch.arange 1 cross 5, except 2 cross 2, A. Okay, it's 1, 2, 3, 4. If I do the max on this, 1. Okay, it's going to return me two things. One is the value, second is the index. Okay, so we are not caring about here what value, because what we want is the indices. Because for our case, the indices are the same as the label. Because like at the 0 index, it's the 0 class. At 1 index, it's 1 class, first class. At 2 index is the second class. That's why we care about the indices. Okay, that's why we'll store its output like this, comma, predicted. Okay, like we are not storing the values in anything. Okay, that's why this underscore, and the indices at our predicted class, which we are storing in the predicted variable. Okay, then we are just going to how many data points we have seen so far. It's just the labels dot size of 0. Spelling error. Okay, and how many correct data points were there? It's just predicted. Okay, and how many of them are equal to the labels that we had? Okay, and this will return like a Boolean thing for true, false, true, false. So some will return me the number, actual number, how many were there. And again dot item to extract the value in this. Okay. So then after this, we are going to calculate the average loss. So average loss is my running loss that I have, okay, divided by the I plus 1. Okay, so whatever the number of batches it's going on with that, because still start from the 0, so that's why we are adding the 1 here. Okay, we have to also calculate the accuracy. Accuracy is basically the correct number of data points divided by the total number of data points that we have seen. Okay, you can multiply it with the 100 to get it in the 100 part. Okay, yeah, so is it clear till now? Okay, so now we can come outside of this for loop. Okay, after that we are going to store our average loss for this batch size in this training loss. So I have the correct indentation. Yes, correct. Okay. We are calculating accuracy inside the loop. We are calculating accuracy inside the loop for see, one more thing was there that Prof used at that time. Okay, this was to show the accuracy at while we are calculating one data point at a time. Okay, while going over each of these batches. Okay, so this accuracy is getting calculated for each of my batches. as this train data loader will give me batches. It's the accuracy for each batch. Okay. Now once that is done, I can all this training loss and loss training accuracy. I hope it's that. Yeah. Train loss dot append average loss and training accuracy dot append this accuracy. Why it's coming in yellow. Train loss is not defined. Okay, train losses. Okay. So once we complete this full epoch across all the batches, we are going to take this average loss and the accuracy, store it in the training loss and the training accuracy. Okay. So once that is done, we will print something here. The epoch that we have. Okay, so we have this epoch plus 1 because it will start from the 0. Okay, and divide by how many epochs has happened. Okay, and here we are going to print the training loss that we have. Okay, so for that we can create one thing here, that is the epoch loss. Okay, average loss that we have got so far, the epoch accuracy so far in one epoch, how much accuracy we got. Okay, these are used to showcase here epoch loss, because from the list it will be a little bit hard to show. That's why I'm going it here. Maybe we can do it here. Training accuracy. Yes, so it's epoch accuracy. Okay, finally we can return the training loss that we have got and the training accuracy. Okay, so try training this model. It's going to take a little bit time. Okay, I just want to check one thing, that whether it gives any error or not. So I think it's not going to give any errors. So yeah, we have to correct it. Okay, so any doubt, anyone? It's going to take quite a while. I think 5 to 10 minutes to complete the training. Okay, to make the training a little bit more visible. Okay, one thing that was not needed, I will stop here. Okay, one thing that was not needed that prof did, so I will copy paste that. No, I'm not using any GPU here. Everything I'm running on the CPU. Okay, one thing that prof did. Okay, I'm going to use that. Okay, that was the progress bar. Okay, so I'm copy pasting the code that I write during the lectures. Okay, what it use, it make use of one library called TQDM. Okay, so the TQDM library, it's basically used to show the progress bar. Okay, TQDM. So if you see the code that we had for that, okay, it's almost the same code that we had, except the part that we have created this extra thing, progress bar. Okay, in the TQDM library. TQDM library, you can just simply import it from that TQDM. Okay, once you do that, you have to just previously we were passing our okay data loader here. Okay, but now we are passing our data loader in this TQDM library. We are passing the total number of data point it has in this loader, and this string, the string will be used to show this progress bar. Okay, and then we are using this progress bar here in the for loop. Okay, other things are same. Okay, the running law of predicted everything is same. Okay, and again in the progress bar, we are setting this extra string to show the accuracy and the loss for each batch when it's getting processed. Okay, and other things are still same.
So please excuse me. Can
Yeah.
we access this Colab notebook, please?
I shared the link already in the chat box.
Okay, thank
Okay,
you.
you can see, I think it was pinned already. Okay. Or else I will share this Colab and the slides that I used in the yesterday session in the discourse. Okay. Oh, I have not run the above function, so let me first run that. Okay. Now if I run this, then TQDM is there. Input T. Okay, yeah. TQDM dot TQDM. Should be just TQDM. Okay, I think it will come here. I will come. One thing, I have one feedback form. If you like the session, you can fill the feedback form to for the help. Okay. I want to complete this. Let me check the code. Should be correct. PPM here. Still this part. So only thing it will show it just that it will show it in the progress bar format, so it will look good to see. Other things it will keep it same. The main logic is same here. Okay, so I hope the main logic was clear. Okay. Any doubt in that part? Okay. Not callable. Adam is callable. Okay. Problem here. Okay, where did we call the optimizer? Zero grade. If I import it without this, set the import statement above. Should work. Same. Okay, now that should come. Okay, and an object is not callable. Okay, train models and loss criteria output. The loss criteria, okay, output. So criteria is an n dot cross entropy loss, okay. This is correct. Model is this, loss is this. We have not missed any step, I hope. Okay, we initialized it, we get the cross entropy loss, and set the optimizer. Okay. and we set this model training loss. Okay. Measure dot zero grade outputs criteria loss dot backward measure dot step.
What is that underscore comma?
Underscore comma, as I said, like for the max values you are going to use, it will return two things: values comma indices. Okay. We are ignoring the values thing. Okay. We only care about the indices part here. Okay, because our indices are our label. Like zero index is basically for the zero label. Okay, that's why those we are storing as in the predicted. Okay, so underscore we are not storing them in the variable. That's why we are using it. Okay. Okay, this I will check it once. So why this error is coming up, but after using the TQDM, okay, the final output should like this. Okay, it will basically show a progress bar kind of thing. Okay. Not sure why this is not coming. Yes, currently here. Okay, got it. I got it. In this current order in which we are calling is wrong. Should like, because in our function the first thing that we are taking is the optimizer and then criteria. Okay. Previously we have passed it at first criteria then the optimizer. That's why it was giving the error. Okay. So now it should work. Yeah, now it's working. Okay, so this was the use of the TQDM. Okay, it was not necessary. It was just that if you want to plot this, progress bar also, then you can use that. Only that you have to make one change here. Okay, instead of using the train data loader in this, you have to use it inside the TQDM. Okay, with the total number of data points and this string. Okay, that string will show up here. Okay.
What is TQDM?
TQDM is the library that is helping us to plot this progress bar here. Okay.
Is it
it's
an
a library.
acronym? It's an acronym.
No, it's not the acronym. It's the library. Okay. It's a library import TQDM. Okay. So yeah. Okay. Now, so it's going to take, as I said, it's going to take some time. It's just 88%, 89% done. But yeah, that's just basically ends our training. Okay. After 5-10 minutes, it's going to stop. Okay. So that ends the demonstration part for the week 3. Anyone has any doubt in the demo part?
What is the difference between the last this piece of code and the one which we did previously?
In the previous, in which do you mean in the one which was giving error?
No, not that.
In that the only thing was that I did not implement this TQDM because it was not necessary. Like
No.
Only
I'm not asking that. What I'm asking is, can you please go a little bit up?
Okay.
Here MNest you have taken and then did right from here. I'm asking the code above this. Just above.
This one.
Above. Yeah, where we were giving batches. Yeah, just a little bit above. Just a little bit above. This is data preparation, not this. This is all MNest. The one above. Yeah.
This one.
Where we were passing it multiple times, right? And yeah, this piece.
Okay, this one is the place where we are defining our model class. Okay, so our entire structure of my model, how many layers and how the flow is happening, and this forward pass function. This is the place where I'm defining my model structure and its forward pass. Okay, now in the below function, I'm using my above model. Okay, to train on my data set. Okay, so this is the training loop. Okay.
So many coding. So this library can put everything inside and then ask us to pass only what is necessary, right? What we give it can be extra for us.
That can happen. See,
In
PyTorch
sklearn,
gives us,
that is how it was, right? For all the
yeah,
libraries, we just pass the necessary parameters and the data set after the
see,
pre-processing.
these models, the deep learning models that we have, these have a different structure rather than from our traditional ML models. First thing, okay. So these models can have different architecture based on how you design. So, okay. So that's why this provides us this class, okay, which can inherit from the ann.module class. So every neural network that we have in the PyTorch you can use or they inherit from the ann.module. Okay. So all the necessary things, okay, like the forward pass, the backward pass calculation, the optimizer calculation, the learning rate scheduler, the dropouts, and how you define the convolution operation, max pooling operation. These all are already defined. Now, only thing that you have to define is the architecture. Okay, so that's what we are defining here above. Okay.
This
So,
architecture can be like a pipeline we can do or something like
yeah,
that.
if you want, see, currently this is like in hard-coded pipeline. Okay,
Oh.
because we have hard-coded that we cannot change it dynamically, like passing some list or something. Of course, you can create that. Okay, you can create a logic here by passing a list to this network. Okay, such that it based on the elements in the list, it automatically creates the convolution layer. Okay, their outputs, etc. Of course, you can create that. I think in the customer churn data set in the week 2 lectures. Okay, for that purpose, Faraz created a kind of dynamic architecture. Okay, I will recommend you to watch that. Okay, in that Faraz used a for loop instead of writing each layer like this. Okay, so that's the only part that you have to do in this class methods. Okay, after that, the rest part is how much time a GPU would take. Okay, if using a GPU and can we increase the number of parameter. If you are using a GPU, of course, it will speed up the training part. Okay, it's going to less than the time now. Exactly how much it's going to take, I cannot tell. Okay, yeah, so it's almost 10 now. 60% is 10, so 40% is remaining. Okay, so please fill the feedback form. I'll share it in the chat. Okay.
Is
Significant.
there any solution for PAs and GAs in the discourse?
Solution for PA and GA are currently under the process for making. Okay, we are making them. So currently they are not available. But if you have any doubt in the PA and GA, you can ask. Okay, I will help you explain it.
So for week 2 is already over and week 3 we are doing. I have I want a little bit explanation for week 2 PA itself. That's why I asked.
Week 2 PA, yeah, you can ask week 2 PA. Because PA does not have deadline, so I can explain.
Okay.
Which question you have doubt?
I have to work on it. I just went
Okay,
through it. So I was not able to pinpoint the questions.
So yeah, you can go through them. If you have any doubt, you can either post it on the discourse.
Yes,
Because I think the next time when we are going to meet, it's the deadline will be over for the week 2.
Yeah,
PA does not have deadline, so you can ask this question on the discourse also. We will answer it there.
Yeah, sure. Thank you.
Okay. Yeah, so thank you everyone. If anyone has any more doubt, general speaking, can we ask GA assignments after the deadline? Yes. After the GA deadline, I in the Monday session, the first thing that we started was the GA only. Rule said not to ask at all. After the deadline, you can ask for the GA. Okay, any question if you have doubt, you can ask. After the deadline, I can discuss. Before the deadline in the GA, I can at max explain the question if you are not able to understand what the question is want to say. Okay, so I can just simplify the question language at max before the deadline, but after the deadline, I can explain the solution also. For the PA, I can do both. Okay. Yeah, I will share the collab and the slides in the discourse. Okay, maybe by tomorrow. Okay. Yeah. And please fill the feedback form.
Thank you, sir. Thank you.
Thank you. Yeah. Okay.
Thanks, Pulkit. Thank you.
Yeah. Welcome.